Hi students, I'll try in this educational video to technologically introduce the principal stresses that can be carried out in a thin-walled pipe, of course as simply and as clearly as possible. Okay, let's go. Well, the pipes, as you can see in the left picture, are considered thin-walled, or more simply thin pipes, when the thickness of the pipe divided by the external diameter of the pipe, call it also the outer diameter of the pipe, should not exceed 1/20. This is the condition of thin-walled pipes. First of all, it's to note that the stresses that can be carried out in a thin-walled pipes are three types: the radial stress, the circumferential stresses, and the axial stresses. And it's to note here that the radial stress can be neglected in the case of thin-walled pipes. And in the next slides, we will explain each type of stress. Well, I start with the radial stress. This radial stress is caused by the pressure applied on the inner side or the inner wall of the shell, and it acts in the radial direction of the pipe. Since the pipe is thin, in other terms, the thickness of the pipe is very small compared to the other dimensions of the pipe, we consider that the radial stress is zero. So the radial stress is neglected in the case of thin-walled pipes. Now let's move to the circumferential stresses, and I will start with the hoop stress. And this hoop stress is caused also by the pressure applied on the inner wall of the pipe, and this hoop stress will act in the circumferential direction of the pipe's material, and the hoop stress is expressed as the pressure multiplied by the outer diameter of the pipe divided by 2 times the thickness of the pipe. The second type of circumferential stress is the torsion stress. This type of stress can occur, for example, as you can see in this figure, when we have a thermal expansion of a vertical pipe. This will act on a horizontal supported pipe, and it will cause a torsion stress in the circumferential direction of the pipe's material. And this torsion stress is expressed as the moment of the torsion divided by 2 times the section modulus. Now let's move to the axial stresses carried out in the pipe's material, and I will start with the axial stress induced by pressure. This pressure is working on the closed ends of a pipe, and it will cause an axial stress acting, of course, in the axial direction of the pipe. This axial stress induced by pressure is equal to the pressure multiplied by the outer diameter of the pipe divided by 4 times the thickness of the pipes, which is of course equal to the hoop stress divided by 2. The second type of axial stress is induced by an external axial force caused generally by the weight loads of connecting pipe segments, and this type of axial stress is expressed as the external axial force, the applied external axial force, divided by the cross-sectional area of the pipe. The third type of axial stress is the bending stress, which is obviously induced by the bending moment caused generally by the self-weight of a supported horizontal pipe. And as you can see in this figure, the maximum bending stress are encountered at the outer edges of the pipe. Of course, this bending stress will act in the axial direction, and it is expressed as the moment of the bending divided by the section modulus. Now I will summarize the different types of stress that occur in thin-walled pipes. So as I said, the radial stress is negligible. Why? Because the thickness of the pipe is considered very small in the case of thin-walled pipes, very small compared to the other dimensions of the pipe. And for the circumferential stresses, we have two types. We have the hoop stress and the torsion stress. Of course, these two types of stresses will act in the circumferential direction of the pipe's material. And for the axial stresses, we have three types. We have the pressure axial stress, the external axial stress, and the bending stress. Well, this educational video takes end. Please, if you have any remarks or suggestions, please don't hesitate to mention it in the comments. Thank you very much.